Right, well, hello everyone, and welcome to another online meeting of the Havering Astronomical Society, and I'm very pleased that you're all able to join us this evening. It's hard to believe that it's over a year ago since we last met together in person at the community centre, before the pandemic put a halt to such gatherings. And I'm sure you thought it was only for a short period of time before things got back to normal. Little did we know. However, I'm quite happy that we have been able to continue with our meetings throughout the time and receive our talks and presentations through this wonderful medium of online video communication. I must say I'm grateful for the efforts of our committee members who made all this possible, particularly Les, Magda and Peter. Not only has this enabled us to maintain contact and interaction with their members throughout the pandemic, but it's also led to us gaining new members along the way. All being well, I'm sure we will be able to meet up in person soon. After our talk this evening, I hope you'll be able to stay with us for a general discussion about all things astronomical. And I'm sure Les will mention it, but please remember to post any questions you may have for our speaker this evening in the chat section. Our speaker this evening is Dr. Greg Brown, who's an astronomer at the Royal Observatory. Greg holds a master's degree in physics with astrophysics and a PhD in observational astronomy from the University of Warwick. During his research at Warwick, he studied some of the largest explosions in the universe and supermassive black holes in distant galaxies. During his time there, he developed a strong passion for science communication and public engagement and shifted career paths, working briefly as an outreach coordinator at the University of Warwick before joining the team at the Royal Observatory Greenwich in 2017, where he now develops the public astronomy programme. I see he's also written a book called Stars, which is the first book in a series of guides written by the astronomers at the Royal Observatory Greenwich. Greg's talk this evening is entitled Black Holes, the Small, the Medium, and the XXL, extra large. So without ado, I'll hand over to you, Greg. Thank you.
Thank you very much. So I will attempt, as always, to share my screen, and hopefully that should now have worked. Please do let me know if it hasn't. The last time I gave a talk a bit like this, these particular headphones that I'm wearing decided to cut out on me about halfway through, which I did not notice for approximately 3 minutes. And this is, of course, where the microphone is as well. So I was talking to myself for about 3 minutes. I will be keeping an eye on the chat, so hopefully that won't happen again. If my mic does drop out, please do shout and I will find out quickly enough. But I won't be able to hear you, just be aware of that. It will have to be through the chat because these will have turned themselves off. Okay, so black holes, the small, the medium, and the extra large. So where to start? Well, I suppose the first thing to start off with is to talk about what is a black hole in the first place. And I say that'll be the start. In reality, that's approximately half the talk this evening because it's actually quite a complicated topic. The simplest answer to that question is that they are a set of extraordinarily tiny objects that have extraordinarily large masses for their size, and their gravity is so strong that if anything gets too close to it, it cannot escape. It doesn't matter how fast it travels, it doesn't matter how hard it pushes, it's incapable of escaping again. And you might think of black holes as being a relatively recent idea, but in fact their history goes back quite a bit longer than you might think. So let's have a talk about that. It actually goes all the way back to these two gentlemen, one of whom you probably know extremely well, of course, Sir Isaac Newton, and his work to try to understand understand what gravity does. Not what gravity is as such, although he was attempting to do that as well, but what he succeeded in doing was understanding, at least to an extent, what gravity does, how it acts on things, what exactly effect it has on other objects. And he came up with his equation for how gravity acts on an object. His idea was effectively that gravity is a force that acts between objects that have mass. So any object that has mass has gravity, and it can pull on other objects that have mass as well. The size of the force that you get is dependent on the mass of the object that's pulling, the mass of the object that's being pulled, and the inverse of the square of the distance between them. Basically, it just means that if you increase the distance between these two objects, the force goes down, and it goes down very, very rapidly. And then a little while later, along came this gentleman, working a little bit later, Reverend John Mitchell. And he was one of the first people to realize, though other people had before, that if light had mass, which was something that wasn't known whether it did or didn't at the time, if light had mass, then it would be affected by gravity. So gravity would be able to bend its path and possibly even reverse its direction. He was the first person in 1783 to come up with the concept of a dark star. And this is basically how dark stars work. Here is a star. A star produces light, and this light gets sent off out into deep space. But what if the force due to gravity on it coming from that star was so strong that it was actually enough to be able to entirely reverse the path of that bit of light coming off of the star? What would that mean? Well, that would mean that no light would be able to escape from that star. And if no light is able to escape from that star, then the star would appear dark. It'd be a star that doesn't emit any light. So Reverend John Mitchell realized that if there were stars out there that were heavy enough, they might be able to completely hide from the rest of the universe because their own light would not be able to escape from them. Now, we now know that this is actually nonsense. This isn't how things work, but it was a lot closer to reality than John Mitchell knew at the time. The person to realize, or to begin to really expand on this and to get us much, much closer to the reality of the situation, is another man that you are probably very familiar with indeed. This is, of course, Albert Einstein, working in the early 1900s to understand something called relativity. Now, relativity is the study of how physics works from different viewpoints, how things appear to other things. And relativity as a subject has been around for an extremely long time because the concept of relativity is something that we come across every day. Say you're traveling in a car along a road. Well, there are two ways of thinking about the situation that you have here. That could be that the car itself is traveling along the road and so it's moving through space. Or alternatively, from the point of view of the driver in the car, that the entire world is coming towards them and they're the ones which are staying still. That idea is the concept of relativity. It's how things appear to different observers. And Albert Einstein at the time was trying to work out how physics is affected by all sorts of different things. He started with his theories of special relativity, which determined how things appear to objects that are moving at different speeds, specifically or rather especially at high speeds. But that wasn't enough. That's where the name special relativity comes from. It's only really applicable under certain conditions. He wanted something that was more widely applicable. And so he wanted to understand how things were affected under acceleration, which is something that wasn't taken into account in special relativity, and importantly, how things were affected by gravity. And the upshot of all of his work, published in 1914, was this. Now, those of you who haven't done any maths past GCSE or O level probably think that looks horrendous. People who've done slightly more maths might think, well, that doesn't actually look too bad, does it? There are only a handful of terms in it, a couple of multiplications, a few fractions. It's not so bad, is it? And those of you who've done a little bit more maths than that will know, no, this is absolutely horrendous. This is a ludicrously complicated and difficult equation, because what you're looking at here is in fact 10 different equations all stacked upon each other, each one of the terms in it having multiple different components which are extraordinarily complicated to calculate. In fact, when Albert Einstein came up with this formula, he never expected anyone to be able to solve it, to be able to come up with some conditions, some answers to what it was that he was seeing. But he could at least describe what this was, what this equation sort of represented. And this is it. This is what that equation effectively represents. It explains what gravity is. And he realized that gravity isn't a force in the normal way that we think of forces, not in the same way as the forces between two charged particles, for example. Instead, gravity is this sort of bending of something called space-time. Isaac Newton had believed that space and time were completely and utterly universal. Everyone agrees on the position of an object. Everyone agrees on the timing of an event. But Albert Einstein realized that wasn't true. Albert Einstein realized that in order to explain all sorts of weird parts of physics that had been noticed even all the way back to the time of Isaac Newton, space and time actually needed to be inextricably linked together in a way that they could not be separated apart. And this led to the construct of space-time, this sort of fabric of the universe, and that everything in the universe is moving through space-time, and that gravity is a distortion, pulling a change in this space-time. So objects with really large mass, like our star that we have here, our sun, they have a huge impact on space-time, a massive distortion. Smaller objects like the Earth have a far more modest distortion, and much, much, much smaller objects like myself, for example, don't have much of a distortion at all on space-time, which frankly I find quite gratifying. But the point is that all of these objects in space, when they distort space-time, they also have to follow space-time. So the Earth orbits around the sun because of this dip in space-time that it has to follow, because it's bound to this surface. Now, it's a bit of a flawed analogy, this whole rubber sheet experiment that is basically what this diagram is all about, but it sort of gets the idea across. But as I say, Albert Einstein did not expect any proper solutions to his equation. It took this guy a month to come up with an actual solution to this equation. And to be fair, it was the absolute simplest equation that you could get, a simplest solution you could get, except for completely empty space. Completely empty space is easy. Everything goes to zero. 0 equals 0 equals 0. Lovely. But The next simplest experiment, the next simplest version of this, is to have a single particle, just one infinitesimally small dot, that would have a mass. And it was this solution that Carl Schwarzschild attempted to work on and indeed succeeded in producing. And it led to this, the concept of a black hole. Because when Carl Schwarzschild was working on this solution, he realized that there were weird, what we call singularities. Now, a singularity in mathematics is just a place where things go to infinity, where numbers can't be defined properly. And that can occur on extraordinarily small scales. That's the sort of singularity you're probably most familiar with. But it can also happen at weird boundaries between two different regions of space. And when Carl Schwarzschild was working on his solution, he realized that there were going to be two singularities in his solution, not just one. There was the same singularity that you have probably heard of, which is what's called a physical singularity. This is where you have literally a dot, an infinitesimally small dot that has a certain amount of mass in it. Now, if you have a finite amount of mass in an infinitely small space, then what you have is something with infinite density. And it was this that was imagined to be the center of Schwarzschild's solution. So he put that singularity there. He knew that was going to be there. What surprised him was what happened just outside of that physical singularity. Because there was this line, this region of space that has now become known as being within the Schwarzschild radius, named after Carl Schwarzschild, where physics would be weird. Basically, if you get inside of this bit of space, the entirety of your future points at the center of the black hole. There's no choice. You haven't got a choice. General relativity works in such a way that your future has to be in the center of that black hole. There's no way to avoid it. And this is what was called a coordinate singularity in mathematics. It's one where if you change the maths that you're using, the singularity disappears, but the function of the singularity is still there. So in this particular case, there is this point of no return that we call the event horizon. If you get too close to this point mass, then you cannot escape it. It is physically impossible for you to do so. It doesn't matter how fast you travel, how hard you push, there is no way back out, because the entirety of your future points at the center of this black hole. Now, black holes actually aren't holes, which you've probably seen on this slide for a little while and wondered what on earth I'm talking about. Black holes are actually one of the worst named objects in astronomy, and trust me, it's got a lot of competition. A lot of competition. Black holes aren't holes because they're actually objects. A hole is the absence of something. It is a hole in a piece of clothing is where the fabric has torn. A hole in the ground is where the ground has opened up and there is now an absence of ground where there once was ground. A hole is the lack of something. A black hole, on the other hand, is actually the presence of something. In fact, it's usually the presence of a lot of stuff. It's all very, very, very small. The reason why it's become known as a hole is because you fall into it. But then again, you fall into the atmosphere and onto the surface of the Earth when you are an astronaut coming back to ground. Or you could fall into the sun. It doesn't mean that the sun or the Earth are holes. And that's where one of these sort of misconceptions has come from. So black holes aren't holes. They are, however, very difficult to make. It's very, very difficult to achieve enough compression to be able to squish something down small enough that the gravity of the object takes over and the whole thing compresses down into this tiny singularity. In order to do it to the sun, which is 700,000 kilometers in radius, about 1.4 million kilometers in diameter, you'd need to squish it down to its Schwarzschild radius, which is 3 kilometers. Something would have to squash the entire sun down to something which is 3 kilometers across, and there is no process that we know of that can do that. So that's the reason why the sun is never going to turn into a black hole, at least as it stands. If you wanted to do it with the Earth, you'd have to squish it down to about the size of a grape, and then gravity would take over and take it all the way down to being a point object, a singularity. Of course, we're not even certain that singularities themselves actually exist. Because light cannot escape from a black hole, we can't actually see into a black hole to see what's there. Which means that it's entirely possible that the blob at the center of a black hole is not a true point mass, not a true singularity. There might be some force out there that's capable of stopping gravity from going further than the event horizon. But we can't see it and we don't know about it. So for now, we work under the assumption that it goes all the way down. And frankly, from the point of view of an astronomer who works on the large scale, it doesn't really matter to me whether a singularity actually exists or not. And yet I've just told you that light can't escape from a black hole, only to immediately go back on that because, as I said, black holes are one of the worst named objects in astronomy, because black holes probably aren't black. Now, we're not going to go into too much detail on this because it's extraordinarily complicated, and frankly, I barely understand it myself, and even that may be overstating things. There's something called Hawking radiation, named after the late Professor Stephen Hawking. He worked a lot on black holes through his career, and he suggested the possibility that it might be possible for black holes to emit something, light, particles, something along those sort of lines, known as Hawking radiation. And it all comes from the idea that particles are constantly being produced and then destroyed out there in the rest of the universe because their energy is just sort of randomly creating particles. And if this happens to happen close to the event horizon of a black hole, then one particle can be absorbed, the other particle emitted, and suddenly the black hole has lost energy. If it's lost energy, then it's also lost mass, which means that, strangely enough, black holes are actually constantly evaporating, disappearing into nothingness. It's just that for the vast majority of black holes that we might be talking about, that takes an extraordinarily long time to happen. So, black holes aren't holes, and black holes, as I said, one of the worst named objects in astronomy. And yet, despite the fact that black holes are some of the most complicated objects in the universe, in the terms of the maths that goes into understanding them, they're also some of the simplest objects in the universe. What do I mean by that? Well, say that you went to the beach and picked up a stone, picked up a pebble. That pebble, a few centimeters across, is made of quadrillions upon quadrillions upon quadrillions of particles. Lots and lots and lots of little bits. And each one of those particles has its own velocity. So they're traveling, they're moving. Each one has its own amount of energy, which is causing it to vibrate. It has its own composition. Maybe one of the atoms will be silicon, another one will be oxygen, and so on and so on and so on. And all of them are put together in this extraordinarily complicated lattice work that produces the pebble that you have in front of you. And then you reach down and pick up another pebble, which looks almost identical to the first, and yet it's incredibly different. It has a lot of particles itself, but they're all rearranged in a different way. They all have their own velocities, their own energies. Even simple objects are incredibly complicated, except black holes. Black holes are really simple. All of that nonsense of particles, and velocities and energies just disappears. It's gone. Everything's just been crushed into this tiny, tiny little object. And that means that the entirety of a black hole, everything you need to know about that black hole, comes from just 3 numbers. Just 3. Its mass, its spin, basically how fast it's rotating, and its charge, by which I mean whether it has a positive or negative charge, whether it had too many electrons or too many protons in it when it formed. Except here's the thing, in astronomy, it's even simpler than that, because the universe is filled with charged particles all over the place. Plasma is absolutely everywhere in the universe. So if there's ever a charge imbalance, charges will move around nice and rapidly in order to get rid of it again. So for astronomy, we just get rid of that last one. 2 numbers. One of the most complicated objects in the universe, and yes, I can completely and utterly describe it in just 2 numbers: mass and spin. This comes down to something called the no-hair theorem, which suggests that all of the complicated information that makes up normal matter is just discarded and lost and never can be found again once stuff passes across that event horizon. So, extraordinarily complicated object, very, very simple to describe it. Now, the tagline for this talk is basically black holes are weird, because black holes are weird. Mainly because physics is weird, but there are a few places where that's more obvious than when we're talking about black holes. But immediately I have to contradict myself by saying it's not that weird. What do I mean by that? Well, you've probably heard the idea in the past that black holes are like huge vacuum cleaners, sucking up all of the stuff in the rest of the universe and swallowing it whole. And plenty of well-meaning astronomers, myself included, have used this to describe black holes in the past. It's a nice shorthand. But the problem is, it sort of describes black holes as being sort of magic. That somehow they are capable of pulling on stuff in a way that we've never seen before. And that's just not true. Black holes pull on stuff in exactly the same way as everything else in the universe pulls on stuff. Gravity. That's all they have. And gravity is determined by mass, which means 2 objects that have the same amount of mass have the same pull of gravity. Here is one of my beautifully drawn, as I'm sure you can agree, one of our diagrams of a star with a planet orbiting around it. Let's pretend it's the sun and our Earth, very much not to scale. The Earth is orbiting around the sun, takes 365.25 days, and it's been doing that pretty much unchanged for most of the 4.5 billion years that the Earth has been around, give or take. Let's say that somehow you were able to entirely replace the sun with a black hole of exactly 1 solar mass. That is the exact same mass as the sun. What would happen? Well, from the Earth's point of view, not very much. The Earth would continue to orbit around the new sun, as if nothing had changed, because the force of gravity acting on the Earth will be exactly the same. We're the same distance away from the sun as we were. We are the same, we're experiencing the same force of gravity as we were. So from the point of view of the Earth, nothing's changed. Granted, every single thing on the Earth would die because there'd be no light or heat getting to the Earth, which would admittedly be not great. But from the Earth's point of view as a planet, nothing's changed. So black holes are weird, yes, but they're not magical. They don't have the ability to pull on objects in a way that other objects can't do themselves. So black holes that have the same mass as a star pull on objects in the same way. The weird stuff happens when you get too close to a black hole. And that's what we're going to focus on now. So black holes are weird. And one of the ways that black holes are weird is that time moves more slowly the closer you get to a black hole. So for the next few slides, I'm going to introduce you to my helpers for today, Sensible Steve and Adventurous Alan. Steve is very much like myself. He loves astronomy, loves understanding things about space and the rest of the universe, but very much a stay-at-home person, not the sort of person to sort of go out there and try to experience things much closer up. Perfectly happy to look through a telescope at objects in the rest of the universe and keep their feet on the ground. Alan, on the other hand, doesn't care. He just wants to explore the rest of the universe. The dangers be damned. So let's see what happens when adventurous Alan, who is decided to go on a journey to this black hole at the bottom here, what happens to him as he gets closer and closer. So due to gravity having an effect on space-time, or to be more accurate, space-time being distorted being what gravity is, that means that time has been distorted as well. And the result is that time moves more slowly the closer you get to a black hole. So as we watch Alan and Steve, who both happen to have absolutely vast clocks on them so that we can see how their time is changing, as Steve watches half an hour go past, Alan sees 15 minutes. But the weird thing is, you've probably seen this on sci-fi shows before, if you've ever watched any sci-fi shows that deal with time dilation and black holes. Everyone sort of starts talking really slowly. And it's almost as though everyone knows what's going on when this is occurring. But that's not true. That wouldn't happen. Alan doesn't notice that time is travelling more slowly. He is near the black hole. He doesn't notice that time's moving weirdly until he looks back at Steve's clock and realises that Steve's clock is travelling too fast. And Steve doesn't notice that things are weird until he looks at Alan's clock and realises it's travelling slowly. So you don't experience time dilation as you wouldn't notice it happening unless you had something that wasn't being affected by time dilation in order to check your times against. You actually see this effect on the Earth. Would you believe it? On the surface of the Earth, time is traveling very, very, very slightly slower than for the rest of the universe at large. But the effect is so incredibly tiny because the gravity of the Earth is so tiny that basically you just don't notice unless you have extraordinarily accurate clocks. So black holes are weird, number one, because time travels more slowly the closer you get to a black hole. Black holes are weird, number two, because of something called gravitational redshift. Now, you're probably aware that light comes in all sorts of different colours. and that if you take white light and split it through a prism, you'll get a spectrum of different colours. Each of those different colours has a different energy associated with it. Blue light is the highest energy type of visible light, the type of light that our eyes can see, and red light is the lowest energy. Conversely, the red light has what's called the longest wavelength, which is basically a measure of how the light is oscillating, how the wave of light is occurring. So it has the longest wavelength, and blue light has the shortest wavelength. Now, the concept of redshift and blue shift is the idea that you can stretch or crush or squash light in various different ways. And one of the ways that we see this all the time, not so much with light, but with sound, is the Doppler shift. This is the effect that you notice whenever a car travels past you on a road. The engine will sound high-pitched on its way towards you and then low-pitched once it's passed by. It produces the meow effect, which is a technical term if ever we've heard one. Now, this also happens to light as well, and light can be changed by the motions of different objects, but it can also be changed by gravity. So as light is moving away from an object with gravity, what it's effectively having to do is drag itself out of a well of gravity. It's having to lose energy to climb its way up out of this object's gravitational pull. And if it loses energy, then it has to shift towards the red, because red has a lower energy than blue light. So a blue photon emitted fairly close to the event horizon of a black hole, but importantly, not at or inside the event horizon, because that light won't reach us. Blue light emitted close to the event horizon of a black hole will become more and more red the further it gets away from that black hole. So it will be perceived as being red to an observer further away. And Alan and Steve will notice this as well. So Steve, far away from the black hole, watching Alan, will notice that this clock that he has is turning redder and redder and redder as he gets closer and closer to the black hole. In fact, he will get so red that his light will eventually be pulled completely out of the visible spectrum. You can go well beyond red light into infrared, microwaves, radio waves, and so on. And that means that Steve will actually see Alan slowly disappear out of existence from his point of view. And he'll only be able to see him if he starts using an infrared telescope or a microwave telescope or a radio telescope in order to be able to see him. And eventually he'll be shifted completely out of the spectrum as he gets pulled all the way to the event horizon, where light will be effectively shifted to infinity because it cannot escape. The interesting thing is that the reverse happens too. So Alan, who thinks he's perfectly normal because he is close to the black hole already, so doesn't notice this blue and red shift, looking back at Steve, will see Steve getting bluer and bluer and bluer. In fact, he'll see the entirety of the rest of the universe getting bluer and bluer as he gets closer and closer to the black hole. And again, blue is not the end of it. Blue can then be shifted out into ultraviolet, X-rays, even gamma rays. So all of the light of the rest of the universe is now being shifted into gamma rays and raining down on top of Alan. So I mentioned that Alan is an idiot. And then it gets even worse, because this is the thing that will probably end Alan. At least as long as we're talking about a relatively small black hole. You may be aware of the tides on the surface of the Earth. The ocean is pulled by the moon. The gravitational pull of the moon bunches up the water on the side closest to the Earth. And sort of because the other side of the Earth is in a sort of a gravity shadow, it's further away, it has less of a pull of gravity on it, you end up with a bulge on that side too, which means that the Earth ends up with 2 tides per day. Any one specific place usually has about 2 tides per day, once every 12 hours or so. Once when you pass through the side facing towards the moon, and once when you pass through the side facing roughly away from the moon. The specifics of tides are actually much more based on the specific geographic location, the shape of the coast, that sort of thing. But generally speaking, 2 tides per day, 1 towards the moon and 1 away. Actually, it's not just the water that does this. It's literally everything. The entirety of the ground actually shifts upwards and downwards by a few meters every day. It's just because everything on your side of the planet Earth is doing the same thing, you don't notice it. But the moon is relatively small, and it's relatively far away, 400,000 kilometers or so. What if instead you had a black hole, which potentially could have a lot more mass than the moon, and because it has no surface, because it has nothing to get in the way, you could get much, much closer to it. Potentially as close as you could want, assuming you'd want to. The result is that the tidal forces on Allen are going to be absolutely vast. If Allen were to fall feet first into the black hole, then the force on his feet would be considerably larger than the force on his head. And this would result in my favourite word in the entirety of the English language, spaghettification, which is where literally one part of you is being pulled downwards faster than the other. And you literally get pulled into, well, spaghetti, which is not pleasant for Allen. So here we have all sort of the different ways that black holes are weird, or at least some of the ways that black holes are weird. One, time is going to be running at a very, very different rate, which means, yes, you can travel far into the future, but it also means that everything else is passing you by as you go closer and closer to a black hole, and there's no way back. So that's great. Number 2, the light coming from you is slowly being redshifted out of existence, so you will eventually disappear. But also all of the light of the rest of the universe is cannonballing down on top of you, converted from the light that it already is into highly damaging gamma rays. And don't forget that because time is running slowly for you and fast for everywhere else, all of that light is coming in much, much quicker. So the entirety of the rest of the universe becomes incredibly bright in gamma rays. And finally, you get close enough and you get torn apart. As I said, Allen is an idiot. Now, black holes come in all sorts of different shapes and sizes. And I'm going to very, very briefly mention the very small, which are not ones which I'm going to be focusing on. These are called microsingularities. And they're not really important to astronomers. Microsingularities are extraordinarily small. They're down to around about 10 to the minus 8 kilograms, or about 22 micrograms. That's about as small as a black hole can ever get. You might be wondering why that specifically is the limit. The reason is that there is this amount of time, you may have heard of it before, it's called the Planck time. The Planck time is basically the shortest amount of time that any physical change can occur for all sorts of quantum mechanical reasons that we won't get into. That is the shortest amount of time that makes any physical sense. And it's about 10 to the minus 43 to 10 to the minus 26 seconds. There's a large amount of uncertainty in it. There are all sorts of reasons why the Planck time has a specific time, but this is the time that black holes might evaporate in. And the reason why this is important is that 10 to the minus 8 or 2.2 by 10 to the minus 8 kilograms is how small a black hole would be to evaporate in the Planck time. So the smallest time that's possible. Evaporation, by the way, happening through Hawking radiation. That's stuff that we talked about very early on. So this is the smallest black hole that can exist, mainly because it's the smallest black hole that we could possibly notice exists, or indeed the universe can notice that it exists, before it completely and utterly disappears. So that is the smallest they get down to. You may have heard of microsingularities when the CERN Large Hadron Collider was turned on for the first time, over a decade ago at this point. There was this concern that the Large Hadron Collider had the chance of producing a microsingularity, a tiny, tiny, tiny black hole. A black hole that, as I've said, evaporates extraordinarily quickly. But that black hole, if it happened in that extraordinarily small amount of time to be able to absorb something else, then it could stay around. It wouldn't evaporate immediately. And the fear was that one of these tiny microsingularities would then, due to gravity, sink towards the center of the Earth and slowly swallow the planet whole. 10 years have gone by, we still seem to be good, so apparently that wasn't a problem. We hope. So let's move on to stellar mass black holes, which are the first type of black holes that actually matter from the point of view of astronomy, because microsingularity is just too small to actually do anything. They appear, they disappear in a tiny fraction of a second. So stellar mass black holes, they are at least about 10, maybe 5, if you can get away with it, solar masses. That's the smallest that they can get down to. And there really isn't anything between microsingularities and those. The reason being that there's no process to be able to create black holes that are somewhere between these tiny, tiny, tiny black holes, microsingularities, and stellar mass black holes. You need to be able to crush stuff down into this tiny, tiny space. And the fact is that stellar mass that's black holes between stellar mass black holes and microsingularities just have no process to be able to be formed. There's no force strong enough to crush stuff down small enough to form a black hole. So stellar mass black holes are where things really begin. And these are formed between about 5 to 80 times the mass of the sun, give or take. And they're formed through the deaths of stars. In fact, they're formed by some of the largest explosions in the universe, supernovae. So when a really massive star, 10, 20, 30 times the mass of our sun, comes to the end of its life, it collapses in upon itself. That's because all of the energy, all of the fuel that was powering it suddenly turns off, suddenly gone. So the whole of the star just collapses under the force of gravity. This causes a rebound that then explodes the star out into space, and that's what we see as a supernova. But that collapse crushed the core of the star. And if it's massive enough, about the 20 to 30 solar mass level, so 20 to 30 times the mass of our sun, then it will be able to be crushed down into a singularity, a point where gravity completely takes over, and there's no force that we know of in the universe that can stop it from collapsing any further. And that's what forms a black hole, a stellar mass black hole. Now, we know that stellar mass black holes, so this is a supernova, by the way, artist impression, as I'm sure you can imagine. And we know that black holes actually exist because we can actually see their effects in the universe. So this is the Crab Nebula. At the center is not a black hole. This is a neutron star instead. It's the core of a star that was above 10 solar masses, above 8 solar masses, but less than about 20. So it didn't have quite enough gravity to crush the core of the star into a black hole. Instead, everything got crushed down into something called a neutron star, an extremely dense object, yes, but nowhere near the level of a black hole. But we can see other objects that absolutely have to be black holes. There are no objects that we know of that can produce this effect. And one of these types of object is something called an X-ray binary. So there are objects out there that produce extremely large quantities of X-rays. They're amongst the brightest sources of X-rays in the night sky. And they, in this particular case, are where a black hole is actually swallowing material from a companion star. Just pulling the material off through gravity, perfectly normal force of gravity, and then accreting it. An accretion is this effect of swallowing this material. As it swallows this material, the material heats up to extremely high temperatures, tens of thousands of degrees Celsius. And when you get to that sort of temperature, you produce vast quantities of X-rays. So that's what these are. These are black holes producing extremely large amounts of light, somewhat again, ironically, considering their name, but it's not the black hole itself which is doing it, or at least producing the light. It's the material around it in this disk that's being slowly swallowed by the black hole that's producing all of this extremely bright light. And a lot of it, as I say, in X-rays. We can also, far more recently, see the effects of gravitational waves. So in 2015, we had the first detection of a gravitational wave predicted by Einstein all the way back in 1914, 1915. And this is where space-time, instead of having just a simple distortion, actually has a whole series of ripples traveling through it as objects are orbiting around one another. And we can look for two objects that are spiraling inwards to merge with one another, to collide with one another. And these could be two neutron stars, a neutron star and a black hole, or two black holes. But the brilliant thing is that gravitational waves have a lot of information stored in them. The ring that we get that comes from these gravitational waves that we effectively hear, sort of, with massive versions of our ears, kind of, in gravitational wave observatories. These are the ringing sounds that you get out of them, or the ringing of this interferometer, as it's called, this gravitational wave observatory, produces a lot of information, including the masses of the objects that fell in and the mass of the object that came out of this collision. And you pile through the maths and you discover that the vast majority of the gravitational waves that we've seen so far can only have been produced by black holes. As far as we know, there's no other object that could have done it. So that's fantastic. We know that black holes do exist. Now, those are the small, the stellar mass black holes. What about larger ones? Oh, sorry, this is a gravitational wave observatory. This is one of these interferometers. And I won't spend much time on this. It basically takes a laser beam, splits the laser beam in two, has it travel along extremely long, and then bounce off a mirror and come back. And then when you recombine the laser, if one of the arms of this observatory was shortened due to a gravitational wave passing through it, then the light will no longer be what's called in phase, which basically means the light won't line up anymore. A laser beam, the light should all be lined up with one another, but if a gravitational wave has passed by, then the light will be slightly out of phase with one another. And you can check that, you can see that effect happening. But the difference that we're talking about is absolutely tiny. It's the equivalent of a thousandth of the width of a proton. It's an incredibly small vibration that we're effectively looking for, which is why they build these things extremely large and have the light bounce forwards and backwards between these mirrors lots of times before collecting it, all sorts of things like that. And here is one of these rings, one of these chirps as they're called, which is the detection of one of these gravitational waves. And this wobble, which you can convert into sound so you can actually hear it, this chirping sound you get has a lot of information stored in it. So we can find out that black holes exist via this method. Not that we were in any particular doubt before the first gravitational wave was detected. Oh, and here's a particularly interesting diagram from a few months ago. It's been updated even more since then, of all of the different gravitational wave detections that we've had in the past. So, well, some of them anyway. And a lot of them have been up at the top. They've been fairly sizable black holes that we actually weren't quite certain how we could make in the first place, and yet there are large quantities of them out there. And then we've got a really weird one down at the bottom, those two arrows going into a question mark at the bottom. That is an object that we don't know what it is. It could be a neutron star, it could be a black hole. If it's a black hole, it's the smallest one we've ever found. If it's a neutron star, it's the biggest one we've ever found. So whichever one it is, it's a really, really interesting discovery. Now then, let's move on to the bit which I know the most about, which is the XXL, the very, very large black holes out there. These are supermassive black holes, and supermassive black holes are actually found at the centers of every large galaxy that we know of in the universe. What you're seeing on your screen at the moment, I hope what you're seeing on your screen at the moment, is a short video of stars at the center of our Milky Way galaxy, observed in the infrared over the course of several years. And it's a little difficult to see, but hopefully you can tell that the stars in the center are moving fast, and the stars towards the outside of this image are moving quite slowly. Now, immediately, that rings true of the solar system. Mercury moves around the sun extremely quickly. Neptune, in comparison, much slower. Not only does it have further to go, it travels more slowly too. So already we're getting an indication that there's some sort of gravity effect going on here. In fact, you can see one of the brightest stars in here actually manages to complete almost a full loop over the course of these few years. And that is a star orbiting around something. But if you do the maths and try to work out where the object it is orbiting around, you've got lots and lots of different stars to work with. Then you discover that actually it's in the middle there, but you can't see it. It's not that flashing thing, by the way. That's just another star. There's nothing there. You can't see anything. And yet, if you run through the maths, the same maths that Isaac Newton came up with all the way back then, you don't even need to use general relativity in order to get this one. Simple classical physics will give you it. You can work out the mass of the object at the center. And it's 4 million times the mass of our sun. It's incredibly vast. And yet you can't see it. It produces no real light. It cannot be seen. It's the only type of object we know that, and that's a black hole. So supermassive black holes are in fact extremely common. As I say, they're found at the centers of almost every galaxy, large galaxy certainly in the universe, probably in every galaxy or almost every galaxy in the universe. We can even see their effect in other ways. We can see in the centers of some galaxies that they're absorbing lots and lots of material, like those X-ray binaries that we saw earlier with a tiny black hole, a few times the mass of the sun, swallowing stuff from a nearby star. Well, here, vast clouds of gas and dust are being consumed by these supermassive black holes and doing exactly the same thing. Massive accretion disk, lots and lots of light Black holes are ironically some of the brightest objects in the universe because of the amount of light being given out by these objects, by the material around some of them. This is what's called an active galactic nucleus, where a black hole is swallowing this stuff. And in this particular image, you can actually see jets of material being blasted out, a bit like water trying to go down a plug hole too fast. Some of it gets spurted back out again. And that's the same sort of thing that we're seeing here. And now, relatively recently, within the last couple of years, we actually have a picture of one of these. This is taken with the Event Horizon telescope, which isn't one telescope, it's actually a whole array of different radio telescopes across the entire world, all working together to produce one single picture of one particular galaxy. In the very center of its galaxy, this is a supermassive black hole. To be more accurate, the supermassive black hole itself is actually in the dark bit in the middle. It's not the whole of the dark bit, it's just part of it. That dark bit that you're seeing is a gravity shadow, a light shadow, where the light from the stuff around this black hole is actually mostly just being absorbed by the black hole before it can reach us, before it can escape. So the stuff around this black hole appears dark, even though there's still stuff there. The black hole itself is actually a fair bit smaller than this. So it's not strictly speaking accurate to say this is the first picture of a black hole, but it is certainly the most zoomed in one that we have. And it fits perfectly with Einstein's theory of general relativity. As far as we can tell, there was nothing wrong with his theory, sort of. It has passed every single test that we've thrown at it with only a couple of minor changes along the way, and it's still going strong. This is an artist's impression of one of these supermassive black holes swallowing material, one of these active galaxies. And the interesting thing is that you can actually use these active galaxies in order to measure the mass of the black hole at the center, and you can then measure the mass of the galaxy as well in all sorts of other different ways. And something weird happens when we look at this. Sorry, this is a diagram of the sorts of things that go into an active galaxy. And this is actually an indication of how bright one of these things is. So I believe it's on the left-hand side of these 2 point sources, these two crosses that you've got here. That's a star. It's in our own galaxy. Top left-hand corner, that is a galaxy. It's about a megaparsec away, something along those lines, so 1 million or more light years away. And then the object on the right, that is a supermassive black hole feeding. And it is even further away than the galaxy we see in the top left-hand corner, and yet by this image it looks almost identical to a star, effectively in our own back garden. So it gives you an idea of how bright these objects can be. And rarely stars and entire solar systems will actually be torn apart by these black holes and swallowed. And this is what the subject of my thesis was: tidal disruption flares, stars being torn apart and eaten by supermassive black holes. And they're interesting because they're like active galaxies that turn on and turn off in a very short period of time. An entire star can be swallowed in a year or two, but an active galaxy turns on and stays on for hundreds of thousands of years. So by studying tidal disruption flares, we have a way to be able to see active galaxies turning on and off in the period of time that a research grant could be given, or, you know, a human life, which is rather useful for us. Oh, and yes, this is strange enough. I worked for 4 years on this thesis, and this diagram is the proudest thing I am of the entirety of the work that I produced, because frankly it looks quite good, and it's gives you an idea of how tidal disruption flares work. So in the first diagram, if a star gets too close, if it travels within the disruption radius, then it gets torn apart. Half the material travels off into deep space and the other half gets absorbed. In part B, we have a partially stripped star. So this is where the star doesn't get close enough to be torn apart entirely, but just part of the outside of the star gets torn off instead. And with C, one of the weird things about tidal disruption flares is the bigger your supermassive black hole is, the harder it is to tear apart the star, because the radius of the event horizon, that point of no return, grows with the mass of the black hole. So if the star passes inside of the event horizon before it's torn apart, which stars can do, then you'll never see the tidal disruption flare. It still happen, it's just no light will ever escape from it. And because the event horizon grows with the mass of the black hole, but gravity, and specifically tidal forces, grow with the inverse cube of the mass, or something along those lines. That means that the event horizon grows faster than the distance at which the star will be torn apart. I'm becoming very aware of the time, so I'm just going to get through the last few slides as quickly as I can. This is just another artist's impression of a tidal disruption flare. Trying to get onto, there we go, that's the bit that I was looking for. So I said a few minutes ago that you can measure the mass of a supermassive black hole using perhaps an active galaxy, perhaps a tidal disruption flare, something along those lines. And you can measure the mass of the galaxy that that black hole resides in all sorts of different ways. And someone decided to plot one against the other, and they realized something odd. The black hole at the center of a galaxy grows with the size of that galaxy. And you might think, well, that sounds perfectly reasonable. Why wouldn't you find bigger black holes in a bigger galaxy? Makes sense, right? Well, no, not really. Black holes, even supermassive black holes, are still tiny compared with the mass of the galaxy that they're in. Usually about 1,000th, 1/10,000th of the mass of the galaxy. They're a tiny, tiny component. It's a bit like going to the beach that we went to earlier and going to another bigger beach and finding bigger pebbles on the bigger beach. That doesn't make sense. You wouldn't expect the size of the pebble to scale with the size of the beach. Not necessarily, at least. So what on earth is going on here? Well, something has to be linking these two. Maybe as black holes feed, they feed compared to the size of the galaxy. Or maybe as black holes feed, they either trigger or stop the formation of stars, or blow material out into deep space, making certain that stars can't be formed, or blow material into itself in order to trigger new stars being formed, or all sorts of other possibilities. But there has to be some sort of link, feedback, between the black hole and the rest of the galaxy, despite the fact that the black hole itself is absolutely tiny compared with the supermassive, compared with the rest of the galaxy. One other really important thing that we do not know much about is how supermassive black holes are formed. We know how stellar mass black holes are formed, the ends of stars' lives, or maybe very occasionally two neutron stars crashing into one another. That could produce a black hole too. But we don't know about the birth of them, of supermassive black holes. Could it be that there were once really massive stars out there, thousands of times the mass of our sun, that produced black holes when they died, and then those black holes grew to the millions, even billions of solar masses that black holes have today? Could supermassive black holes grow faster than we think they can? There is effectively a limit on how fast black holes can grow. As black holes absorb material, they produce light, but light can actually push against stuff, like the stuff that they're feeding on. So if you feed on too much stuff, you produce too much light, that pushes away the stuff that you're feeding on, and the feeding stops. So there's a way of sort of regulating how fast black holes can grow. Maybe supermassive black holes can grow faster than this Eddington limit, as it's called. Can galaxies just spontaneously produce black holes by having the cores of those galaxies merge and produce one massive black hole very early on? Or did the Big Bang itself produce the seeds of these black holes, little bits of the universe that were too dense and collapsed in upon themselves before they had time to expand outwards with the Big Bang and create the universe that we see today? The fact is, we don't know. And one way to solve it would be to find something called intermediate mass black holes. And intermediate mass black holes are the medium. And we haven't found any, which is a bit of a problem. We've got some candidates, maybe some possibilities, but the fact is, we just don't know. So maybe one day we'll have all the intermediate mass black holes, be able to find them out in the rest of the universe. Maybe they are the missing link that solves our problem and explains how black holes were formed. But right now, we don't really know. Maybe. And it's hoped that things like the Large Synoptic Survey Telescope, which has recently been renamed as the Vera C. Rubin Observatory, and satellites like SWIFT, which I use for my own thesis, will be able to find lots more of these tidal disruption flares, these active galactic nuclei, and maybe these intermediate mass black holes as well. But that's where I'm going to leave that now, and I'll be very, very happy to answer any questions that you may have. So thank you very much.
Excellent. Well, Greg, thanks very much for taking us on the tour of the world or the universe of black holes. And I think we should, I'm going to unmute everybody and invite everybody to show in our normal way our appreciation for Greg and his wonderful talk. So thanks very much, Greg. Right. So we do, I mean, not surprisingly, we do have quite a few questions. How are you for your time, Greg? I'm just conscious of.
I'm here basically until the end of the session. If you want me to be, that's no problem.
Okay, perfect. All right. Well, let's see if we can work our way through some of the questions. And the first question from Andrew: on the way to formation of a black hole, is there an intermediate neutron star stage?
Right. Okay. So a very good question, and one that I'll be entirely honest, I'm not entirely certain of the answer to. What I do know is the formation of a black hole during the supernova is extremely fast. So technically speaking, yes, I guess there is, for a short period of time, some time when part of the core of the star has been crushed down enough that it would be counted as a sort of a neutron star object, but hasn't quite yet reached the density required to shrink all the way down into a black hole. But my suspicion would be that such a period would last for such an incredibly short period of time that it wouldn't be reasonable to refer to it as a neutron star in of itself. It just would be a time when you're halfway between having a normal core of a star, albeit an extremely massive one, and a black hole. So yeah.
Okay, great, thank you. And how does what happens to time inside a black hole?
Okay, so this is one of the things that's probably the most complicated for us to to understand. The simple answer is that we don't know as such, because we can't observe it. And what you want to understand is that relativity works by observing things from other viewpoints. So relativity is the study of how things appear to other things. So if something is unobservable, then the whole field of relativity effectively falls apart. We don't know what happens inside of a black hole. We don't know exactly what happens inside the event horizon of a black hole. all we can say is that time slows from the perspective of an external observer right up until the point where it hits the black hole's event horizon. And then, at least in one reading of general relativity, it takes an infinite amount of time for Alan to cross the event horizon and disappear into non-existence. That's only one reading of general relativity. In reality, it probably takes a finite amount of time, but there are all sorts of reasons why that is, which are frankly well above my head.
Okay, excellent. Very close on to as you mentioned, Alan. If Alan wouldn't notice the time dilation that occurs when he gets closer to a black hole, would he notice the effects of spaghettification?
Oh yeah, yeah. he noticed spaghettification, absolutely. So the thing about the thing about time dilation is that it's a relativistic effect. So again, it's something that is in comparison to something else. Whereas tidal forces are just something that happens. And if I take an object and I pull it into pieces, everyone now agrees that thing is now in pieces. It doesn't matter what your perspective is. Now, they might disagree on when it happened, they might disagree on where it happened, but they don't disagree on what happened. And that's the difference there. So Alan absolutely would notice himself being literally torn to shreds by the supermassive, by this black hole. Yeah.
Unfortunate Alan. Right. How do we know that time slows down?
Well, we can actually measure it. So we know that it happens on Earth already. So we can see the effect if we. So we've done it with both special relativity and general relativity. If you take a clock, two atomic clocks, extremely precise, very, very well calibrated, and you take one to the top of a tall mountain, for example, and leave it there for a long period of time, and then bring it back down and compare it with the clock that was at sea level, then the times will be different. The one at the top of the mountain will have traveled slightly further into the future than the one at sea level. So we know that this effect does happen from direct experimentation. We can also see the effects of time dilation on things that are happening close to a supermassive black hole, for example. So we can see flaring in a black hole. So if the accretion disk, this material around the outside, if it has lots and lots of flares going on inside it, which this is a violent process, it will be flaring. You can see the effect of time dilation on those flares. It's definitely occurring. We can see it experimentally as well as theoretically.
Yeah, what always amazes me is even the chemical processes will slow down as well. It's just
absolutely everything.
Okay, what happens if two black holes merge?
They become a bigger black hole is basically the short answer to that one. The exact physics of what happens to the event horizon as the two things are colliding, I attempted to understand when I was doing my thesis, when I was doing my PhD and I was doing my research. I must admit it went in one ear and out the other because it's really very complicated. It basically becomes a larger black hole. And so I showed you that diagram of some of the detections made by LIGO and Virgo, these gravitational wave interferometers across the planet. And some of those were definitely black hole mergers. So where you've got 10 or even 20 solar mass black holes combining together to produce much, much larger black holes as a result.
Great, thank you. You showed the diagrams of the accretion disk and the radiation given off and all that sort of thing, and there were the jets coming out. How are those relativistic jets formed? If everything's going in a sort of circle that way, and then these are things that are coming out that way.
Yeah, what you have basically hit upon is one of the biggest open questions in in accretion physics at the moment. The simple answer is we don't know. It might be connected to, in fact, we think it is connected in some way to the spin of the black hole. But how you get energy out of the spin of a black hole, we don't know, but somehow they are. We think it's probably connected to the magnetic field of a black hole, but how a black hole even necessarily has a magnetic field, we don't know. So frankly, it's extremely complicated. There are three ways to get a groan in an astronomical conference. That's to ask, how does dust affect your results? How do magnetic fields affect your results? And are there any jets? And all three of those is just because they're so incredibly complicated, and they two of them just get in the way for the most part, and the jets are just ludicrously complicated.
Right. Okay. Well, perhaps sometime in the future you can come back and answer that one. Do gravitational waves affect the Earth? This is from
Yeah, it depends what you mean by affect the Earth. The simple answer is yes, absolutely. There are gravitational waves passing through us right now. Absolutely any motion whatsoever of an object that has mass has an effect. So me doing that is actually producing a gravitational wave, and because you are extremely close to me, you are in fact being affected by that gravitational wave. It is passing through you as I'm doing it, or within the light lag time to wherever you are, which, considering you're probably not very far away at all, is extremely short. So almost instantaneously, that wave is passing straight through you. Am I coming through? I've just had an alert that my bandwidth is very low.
Yeah, there's a bit of stuttering, but you're okay. Can hear the audio fine.
I have no idea, unfortunately, if I'm coming through at the moment.
Yep, keep talking.
You're coming through very, very... keep talking. I will keep talking. That's fine. Okay, so yes, but even gravitational waves from is absolutely minuscule gravitational waves, extremely small, and that means that you would not notice them unless you had an extremely carefully controlled experiment like LIGO or Virgo set up to be able to measure them. As I said, we're talking fluctuations in distance which are extremely small. If you had a beam of light the entirety a light year long, the fluctuation of that beam of light would be about the width of a human hair. That is the sort of precision that these experiments are working on. Incredibly small.
Yep. Okay. Before we have the last couple of questions from the WebEx chat, we've actually got one from our YouTube listeners. One's come in. Black holes are characterized, as you mentioned, by mass and spin. But how is the diameter of the event horizon related to its mass?
Sorry, would you mind sort of repeating that? I got almost all of it, but if you could repeat it one more time, that'd be great.
Yeah, let me just hang on. See, just in case, I'm going to copy it over into the chat.
Pop it into the chat. It's a good plan. Yeah.
There we go. Black holes.
Black holes are characterized by mass and spin only, but how is related the diameter of the event horizon to its mass? So it scales proportionally. So if a black hole is twice as massive, the radius of its event horizon, or the diameter of its event horizon, is twice as big. And as I mentioned, this actually produces a rather weird effect, which took me a bit by surprise early on in my PhD when I realized that this was the case. Small black holes appear to be considerably more violent than large ones. What do I mean by that? Well, say that Alan decided to take a trip to a small black hole. horizon, he's extremely close to it. And that means that the difference in the force of gravity on his feet compared with his head is huge. And so he gets spaghettified. But say that he approached a supermassive black hole. Supermassive black holes can be larger than our entire, the event horizon can be larger than our entire solar system. It can be utterly vast. And that means that when Alan approaches the supermassive black hole, the force on his feet is actually not that different to the force on his head. He could be perfectly comfortable. It might be similar to the force between my own feet and my own head standing here on sitting here on the Earth. Absolutely tiny. Which means that Alan could perfectly well survive passing across the event horizon of a supermassive black hole, but would not survive passing the event horizon of a small black hole. The important point here, though, is that that doesn't mean that Alan manages to avoid being spaghettified. It's just we don't see it. It happens, but it just happens much, much closer to the singularity of the black hole, past the event horizon, where we can't see.
Great. Okay. And last couple of questions are a couple of interesting ones here. Are black holes the starters of galaxy formation? Did you get that?
Are black holes the starters of galaxy formation? Yes, I did get the question. Sorry, I apologize. This is my internet playing up, I'm afraid. So are black holes the starters of galaxy formation? Very good question. We don't know. It all comes down to basically where do supermassive black holes come from? And because we don't know where supermassive black holes come from, we can't be certain that they form the seeds at the center of a galaxy. Most likely the answer is no, because as I've already said, the mass of a galaxy is much, 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 much larger than the black hole. And it seems unlikely that they'd be able to act as the seed for the entirety of the formation of that black hole. Instead, dark matter is probably the cause of that, and something called overdensity, which is where you have a fair amount of stuff crammed into a relatively small space, enough that it starts to collapse down. But when I say relatively small space, I mean even larger than the size of a galaxy. It's just you need enough stuff in that region for gravity to start collapsing things down and create a galaxy in the middle of it.
All right. Okay. And sorry, I skipped over one question earlier. How does one distinguish a gravitational redshift from a radial velocity redshift?
With difficulty is the answer to that one, because they basically have the same effect. They look very, very similar. Basically we do it based on the situation of the object that we're looking at. So if we see the interesting thing about gravitational redshift is that light that's attempting to go in the wrong direction, so light that's going in the wrong direction from us and then starts to loop back, will also be affected by this gravitational redshift. And that will, if we look at the spectrum of an object, which is splitting out all the light into its different colors, then this can cause specific lines, usually dark lines that we call absorption lines in the spectrum, to widen. And that's one way that we can tell that gravitational redshift is happening, because we can see gravitational redshift as well as shifting the line across. Relativistic redshift doesn't do that. Relativistic redshift, as long as the object is basically all moving in the same direction at the same speed, you effectively get the same shift in all directions. But then again, you can get widening due to radial velocity redshift as well. It's complicated is the simplest answer, I'm afraid, to that question.
Right, and really the final question, Greg, because you've done really well in tackling all the questions so far. You mentioned briefly a moment ago dark matter. Can black holes absorb
Indeed.
dark matter?
Okay, so honestly, I don't know. I do not know if anyone knows. From the sort of a naive idea, the answer would have to be yes, because as far as we know, dark matter is a type of particle, a weird type of particle to be sure, but nonetheless a type of particle that exists in the universe in the same sort of way as all sorts of other different things, except that it is all but imperceptible except through gravity. Now, because general relativity effectively just encompasses the entirety of this topic of gravity, if dark matter is affected by gravity, and we know that it must be, then it should therefore be affected by gravity of a black hole. It should follow the rules of all of the rest of the matter in the universe when it comes to getting too close to a black hole, falling in and being absorbed by the event horizon and not being able to escape again. It shouldn't be possible, from my naive understanding, for it to disregard those rules. Is even weirder than we think it is, and maybe somehow it can avoid that fate. But my very strong suspicion would be no, it can't. And that it would just be crammed down into whatever there is at the center of a black hole, whether that is a true singularity or just a blob.
Great. Well, on that enigmatic question and enigmatic answer, I think we'll draw a close to the Q&A section. I think just checking, we haven't had any other questions on our YouTube feed. So once again, Greg, I think actually everybody, if you can unmute yourselves, if we can just show Greg a normal appreciation again for all the Q&A as well. So thanks very much for a great talk. Thanks very much for joining us.
Thank you.